All right, so today we're going to have a look at geometrical proofs using vectors. So vectors are very useful for proving certain geometrical properties, especially proving properties involving parallelograms and things in right angles. It often helps us solving things using circle geometry, and we can prove lots of different things such as the midpoints of the sides of a quadrilateral, or the sum of the lengths of the squares in a diagonal. So constructing proofs using these geometric properties, or proving these geometrical properties using vectors, can be quite tricky and a bit abstract, but once you get used to it, it starts to get a bit better. So to prove theorems using vectors, there's no rules, and you can often prove the same thing using vectors multiple different ways. But there's a few rules that will help you. Number one is we always begin by drawing a diagram and labeling all points. We then want to introduce the vectors. It might be one of the vertices or a point outside the figure, and often they will be defined for us in the question. We might know that the sum product of vectors to complete a triangle, so the sum of vectors in a triangle is 0, because if you start at vertex A, move all around a triangle, get back to A where your displacement's 0. We might want to use the fact that parallel vectors are multiples of each other. The dot product is 0 when vectors are at right angles, or the dot product may allow us to access cos theta. Some other things that aren't written there are, on a parallelogram, for example, the vectors on corresponding parallel sides are the same vector. So example number 1, we've got in triangle OAB, we've got OA is A and OB is B. Now automatically when I'm reading this question, before I finish reading the question, I label my diagram. So OA is A and OB is B. I label my diagram as I'm reading the question. Given that point P and Q are the midpoints of OA and OB, so I might want to add this onto my diagram. Express PQ and AB in terms of A and B. Okay. Well, first of all, PQ, the vector PQ, well, we're going from P down to Q, is going to be OQ take away OP. Now, if B is the vector going all the way along from O to B, then this vector is B on 2, and this vector is A on 2. So OQ is B on 2, and OP is A on 2. So this is the vector 1/2 of B minus A. And then if we have a look at AB, well, AB is just going to equal, we're going from A down to B. AB is simply going to be OB minus OA. Now, OB was defined in the question to be B, and OA was A. So therefore, we can see, we're asked to state the geometrical relationship between PQ and AB. Well, we can see, we've just figured out that PQ is really a half AB. So therefore, AB is double PQ. But really they're the same vector, they're parallel vectors, one is just doubled than the other. Okay. Example number 2, we've got, in the diagram, OS is equal to 2R and OQ is equal to 3 on 2P. Given that QK is MQR and PQ is NPS, find two distinct expressions in terms of P, R, and M for OK. By equating these expressions, find the values of M and N, and hence calculate the ratios of QK to QR and PK to KS. Okay, something that potentially I may have missed when I wrote down this question, but it's not explicitly stated, is that even though this whole vector along here is 2R, this vector here from O to R is R. It might be obvious from the question, but it's not really explicitly stated. If all across is 3 on 2P, then we're going to say, okay, from O to P is the vector P. Now let's add some stuff to our diagram. We're told that QK is equal to MQR. We'll add that to our diagram. We're also told that PK is NPS. Let's add that in. NPS. I might make that a tad bigger. NPS. Right. Now we're trying to find some unique or two distinct expressions for OK. I'm going to add in that vector OK. And we're trying to find two expressions for OK. Now we're asked to find these expressions just in terms of N, M, P, and R. Let's have a think of what these two expressions for OK might be. First up, we're going to go along OP, and we're going to plus PK. That would get us to OK, so we're going to go along OP and plus PK. That's our first expression. A second expression, well, we could go all the way up here. So all the way up there, we're going to have OQ, and then down here, we're going to plus QK. So those are our two expressions for OK. And we're going to try and manipulate those to have expressions in these that only involve P, R, M, and N. We might first of all figure out some expressions for QK and PK, so these two things here. Well, we know, for example, PK first up. PK is equal to N times P of S, or PS. So let's find PS. PS is this vector here. And that vector is going to equal R minus P. Not R minus P, sorry. It's going to equal 2R minus P because we're going all the way along OS. 2R minus P. So we're going along 2R. We're taking away P up there. Right. So that's PS. Let's have an expression for QR. So we know that QK, which is the thing I've highlighted in blue that we would like to find, but we know that QK is MQR. So let's find QR and see what that gets us. So QR, that's going to equal, we're going from Q down to R. It's going to equal R minus 3 on 2P. And that's because that whole vector, QO, going all the way down here, is 3 on 2P. We're told that in the question. So we're going R minus 3 on 2P. Right. So we've found expressions for PS and QR. So what we might do is manipulate some of these expressions here. We know that OP, we're going to leave that there for example, but we know that PK, we're told in the question that PK is equal to NPS. We're also told in the question that QK is equal to MQR. But we've just derived expressions for PS and QR. So let's say this is OP plus N times by PS we figured out was 2R minus P. And this one, we've got OQ plus M times by, we just figured out that QR was R minus 3 on 2P. Right, we're almost there. We're going to get rid of our OPs now, our OP and our OQ. So OK, just having a look at the first expression, OK is equal to, now OP is the vector P. So we've got that there. OP is the vector P. And we've got plus 2 times NR minus P. one expression. Now a second expression, okay, well OQ, that's that thing here. OQ, just I might highlight this OP there and that P there to show they're the same. So OQ is equal to 3 on 2P. We're told that in the question. So 3 on 2P plus MR minus 3 on 2P. Okay. And I'll highlight that is the same as the thing above it in blue. Now, we're told in the question we're going to, by equating these expressions. So we're going to equate these expressions. What we might do first of all before we equate these expressions is expand and factorize and get some expressions where we've just got P outside of brackets and then our N's by themselves. So let's expand this. So 2NR minus NP. Now I'm going to take out a factor of P and I'm going to have 1 minus N plus 2NR. That's one expression. Our second one, well, let's expand. So 3 on 2P plus MR minus 3 on 2 MP. Take out a factor of P again. So P, 3 on 2 minus 3 on 2M plus MR. Now the question tells us to equate these two vectors because okay, they're both okay, so they're the same thing. So that means that P, 1 minus N plus 2NR is equal to P, 3 on 2 minus 3 on 2M plus MR. Now this is where it's really going to test your fundamental understanding of vectors, because we know that vectors are, like vector P and vector R are different things. So what that means is everything involving vector P on the left-hand side has to equal everything involving vector P on the right-hand side. In other words, this stuff has to equal this stuff, and this stuff has to equal that. So that's going to give us two equations. Number one, 1 minus N is equal to 3 on 2 minus 3 on 2M. And another equation, 2N equals M. So if we have a go of simultaneously solving these, we're going to have, let's replace our M with 2N. So 1 minus N equals 3 on 2 minus 3 on 2 times by 2N. So 1 minus N equals 3 on 2 minus 3N. Times everything by 2. We're going to have, going up here, timesing everything by 2. 2 minus 2N equals so 2 minus 2N is equal to 3 minus 6N. We're going to plus 6N to the other side and minus 1, so 4N is equal to 1 and N is equal to 1/4. And that would make M equal to 1/2. So I've now found the values of M and N. Now I want to find those ratios of sides. Now, if we look at N, for example, we figured out N was 1/4. So N, we're going to have a look, okay, that's 1/4 there. Now N is going to be 1/4 no matter the size of this vector. Now if PS is this whole vector I'm about to do in green, well, if PK is 1/4, then the rest of the vector has to be 3/4. So the ratio of PK to KS is equal to 1/4 to 3/4. Or that's the ratio 4 to 12. So that's our first ratio there. We have a look at our second ratio. I might rub this green stuff out now. Have a look at our second ratio, which is our M. Now we figured out M was 1/2. So again, no matter the size of the vector, the ratio is still going to be the same. It's always going to be a half. So if QK is a half, well, that would mean QR is the whole vector. So KR has to be 1 minus a half, which is a half again. So the ratio is a half to half, or 1 to 1. So the ratio of QK to KR is a half to a half, which is 1 to 1. And that's our answer there. So question number 3 says OXYZ is a parallelogram. We've got M is the midpoint of XY. Now I've just added to this diagram, if OX is 8, 0, we're told that in part A, that means that ZY is also 8, 0 because it's a parallelogram. And in a similar fashion, since OZ is minus 2, 6, then XY is also minus 2, 6. So part A asks us to find first up what vector XM is equal to. Well, since we've figured out XY is minus 2, 6, and we're also told that M is the midpoint of XY, then XM is going to just be half of the vector XY, or half of minus 2, 6, which is minus 1, 3. Part B, we've got given ON is V times ON, write down in terms of VON. Well, we're told in the question that ON is equal to V times by OM. But we only want it in terms of V, not in terms of OM. So we might figure out what on earth vector OM is. OM is simply going to be the addition of OX plus XM. Now OX is 8, 0, and XM we figured out already was minus 1, 3 in the previous question. So we add those two together and we get 7, 3. Not 7 on 3, 7, 3. So OM is 7, 3, which therefore makes ON equal to V times 7, 3. And we're done. Part C says, given that ON is equal to OX plus WXZ, write in terms of WON. Let's have a go at that. So we've got ON is equal to OX plus W times by XZ. So we're going to have a look at what on earth, first of all, OX is equal to. OX, we're told in the question, is 8, 0. Plus W, we're going to have a look at what XZ is equal to. Now, XZ, we've actually already found out what XZ is. We found that out in previous part, which I actually forgot to do. So XZ we didn't do, which was up here. So we might do that now. So XZ, just from part A still, XZ is going to equal the vector ZO minus the vector XO. So that will get us the vector minus 10, 6. So substituting that back into part C, so minus 10, 6, which is equal to the vector 8 minus 10W, or 6W. Now that's equal to the vector ON, which we already figured out was V times by 7, 3. So now we're asked to, so we figured out, first of all, part C. That was this right here. And part D asks us to equate these two simultaneous equations, or create simultaneous equations to find the values of W and V. So here we're going to equate the x's on both sides, and then separately the y's on both sides. So 7V is equal to 8 minus 10W, and we've also got 3V is equal to 6W, or V is equal to 2W. So if we substitute that back into our original equation, we get 7 times 2 is 14W equals 8 minus 10W, which means 24W equals 8, and W is 1/3. Now that would make V 2/3, timesing both sides by 2 by substituting that into V equals 2W. Alright. This next question, we're told that the ratio of OA to OC is 1 to 2, and OB to OD is also 1 to 2. So we might write down what those ratios mean. If OA to OC is 1 to 2, that tells us that OC is equal to 2 times by OA. In other words, OC is twice as large as OA, and that makes sense. It does look like on the diagram that it's twice as large. Also from the diagram, it's telling us that OD, well, it's in the ratio with OB is 1 to 2, and it's equal to 2 times by OB. But we're going to consider the signs of the vectors because, yes, OA is twice as large as OC, but they're actually going in opposite directions. So if we were talking about the magnitude of these vectors, we would be fine. But since OC is going in the opposite directions, we're going to have to put minuses here and here for those statements to be true. If we were just talking about the magnitude of the vectors, say we had absolute value signs on either side, then we would be fine, but we have to make sure we're considering the value, the direction of these vectors. So part A, we're going to find AB, OC, OD, and DC. So AB, now we've got x and y in the question, so let's use it. AB is x minus y, y minus x, which is OB minus OA. So that's AB there. Okay. OC, let's have a think about what OC is equal to. We should already figure that out at the top. OC is minus 2 OA, and OD is minus 2 OB. So we've done those two. Now we're going to find DC. Now DC is going to equal, so DC is from here over to here. It's going to equal OC minus OD. But we've already figured out that OC is minus 2 OA, and OD is minus 2 OB. So if we have a go at expanding that minus, we're going to have 2 OB minus 2 OA, which is taking out a factor of 2, OB minus OA. Now we've already figured out that OB minus OA is AB, so this is 2 times the vector AB. So DC is equal to 2AB. So that's what the question was asking us. How are A and B and DC related? We'll go therefore DC is double AB. And we're done. Okay, question number 5. We're asked to, we're told, that OABC is a parallelogram, and the ratio of OD to DC is 1 to 2. And we're finding AB, OD, and BD, and we're going to do that in terms of x and y. Okay, AB is nice and easy. AB is simply y minus x. And OC is also y minus x, and that's because it's a parallelogram. So AB going up here is going to be the same as OC going across there, so it's y minus x. Now we're told the ratio of OD to DC is 1 to 2. So what that's telling us is OD, and then we've got DC here, the ratio is 1 to 2. In other words, 2 times by OD is equal to DC. Now, we also know from the diagram that the vector OC is equal to OD plus 3DC. OD plus DC. So OC is equal to OD plus DC. But we already know that DC is equal to 2OD. So this is OD plus 2DC. So therefore OC is equal to 3 times by OD. Alright, now we're trying to find at the moment, we've found AB in terms of X and Y. We're trying to find OD now in terms of X and Y. So OD, if we rearrange this, is 1/3 of OC. But we already know that OC is Y minus X, so it's 1/3 Y minus X is OD. Last one, we're trying to find BD. Now, if we look where BD is on this diagram, it is that vector right there. So BD, just without X and Y, BD is equal to minus Y, so going across down Y, and plus OD. Which is minus Y. We already figured out that OD was 1/3 Y minus X. If we have a go at expanding that, we're going to have BD is equal to minus 2Y on 3 minus X. Alright. Last example for today. So we've got, in the quadrilateral, OA is equal to 2A, OB is 2B, OC is 2C. The points Q, P, R, and S are the midpoints of the sides OA, OC, and BC respectively. And we've got to express in terms of A, B, and C quite a number of different things. We might want to add a few things to our diagram. So we want to find, first of all, AB, but we are told, for example, that 2A, the vector, we've got the vector OA, but we're told P is the midpoint of vector OA. But if OA is also 2A, that makes this vector A and this vector A, since it's halfway in between. And this is vector C here, and this is also vector C here, because it's 2, the whole thing is 2C. Alright, so part 1, we're trying to find AB. So AB is going to equal, so we're going from A up to B. Remember, it's the head of the second vector to the head of the first vector. So 2B minus 2A would be that vector there, AB. Part 2, BC. BC, well, we're starting at B and we're going across to C. Well, same idea, the head of, we're going from here up to here, it's the head of the second vector, so minus 2B, to the head of the first, 2C. So 2C minus 2B. Okay, part 3, PQ. So we're going here, P, and up to Q. Well, we already know from P to A is A, because from P to A it's the midpoint of the vector OA, and OA is 2A, so half of it is A. So PA is going to equal, first of all, the vector A, plus, to get up to Q, if you're standing at A to get up to Q, you're going half of AB. We already know, though, that AB is 2B minus 2A. So A is equal to PA is equal to A plus B minus A, which is equal to the vector B. So PA is the same as vector B, and that does look like that on our diagram. This vector PA does look like that vector there, so that does make sense. Okay. Part 4. We've got to find QR. So we're starting at Q, and we're going across to R. Well, if we have a look at what we're actually doing, so we're going to get from Q, we have to go up to here. Now that's just half of AB again, because Q is the midpoint of AB. So QR, first up, is equal to a half AB plus a half of BC because R is the midpoint of BC. Now we already figured out what all of those things are. So AB was 2B minus 2A, and BC was 2C minus 2B. So expanding all of that out, we're going to have B minus A plus C minus B. So the B's will cancel, and we're going to have C minus A, which is QR. So that's C minus A. And part V, we're finding PS. So PS, rub out some of this. PS is that. And that's actually going to be, well, we're going across from O to P, and we've got O to S. The head of the second vector, which is A, to the head of the first C. So for part 5, we're actually going to have C minus A. Now we're describing the relationship first up between QR and PS. Well, this here is equal to PS, and we already figured out that QR was also C minus A. So for part B, that they're the same vector. Let's add that onto our diagram. Actually, before we do that, we might read part C. What sort of quadrilateral is PQRS? Let's add PQRS. So P to Q, might do that a bit better. P to Q, then up to R, over to S, and then down. So it's looking like some sort of square. Now we just figured out that these two vectors were the same. Now, if those two vectors are the same, that actually means that the other two sides also have to be the same. Because, remember, vectors, for vectors to be the same, that means not only do they have the same magnitude, but they also have the same direction. So if PS and QR are the exact same vector, that means they have the same magnitude and the same direction. Now because of that, it means PQ and SR also have to be the same vector. Now we can't say for certain that it's a square, but we can say that it's a parallelogram. To say it's a square, we would have to know the value of the vectors so we could determine the angle between the two vectors using our cos theta is the dot product over the magnitude product. But we can't do that, and we'd have to prove that they're at 90 degrees or they're orthogonal, which we can't do, so we can only say it's a parallelogram. Okay, thank you for listening. I hope that makes sense.